Good morning, everybody. Let me see if I can get this a little closer. I think that's a little better, isn't it? Okay, so today we are starting a new chapter, chapter 15. We were on chapter 14, and now we're on chapter 15. There are only 2 sections in chapter 15. It's a fairly short chapter, so we will have another test before Christmas. So in this chapter, we're looking at the classification of matter. And section 1, we talk about what matter is made of, the composition of matter. Now, the main idea here is that matter exists as one of 2 things: either a pure substance or as a mixture. So matter exists as one of 2 things. It's either a pure substance or it's a mixture. And we're going to look at the different things that you can have as substances or as mixtures, okay? And you'll notice this particular set is nice and colorful. I like that. I like a lot of color, so I'm liking this one. The first one I want to look at is a substance. What is a substance? A substance is simply any type of matter with a fixed composition. A substance can be one of 2 things. It can be an element or it can be a compound. Now, let's see what those are and what some examples of each would be. An element is a substance that is made up of atoms that are all alike. Underline that right there. Atoms that are all alike. There are no other kinds of atoms but just the one kind of atom. So some examples would be a copper wire. Okay, it's pure copper. All the atoms in the wire are copper atoms. There are no gold atoms mixed in or iron atoms. It's all copper. Helium. Like in a tank of helium gas you use to fill balloons. Inside the tank, the atoms are all helium atoms. There are no oxygen atoms or other sorts of gas atoms mixed in. They're all helium, one element. Iron. Okay, if you have a fireplace in your house, your parents may have a poker to use to push the logs. A poker is made of iron, pure iron. Okay, nothing else mixed in. All the atoms are iron. In fact, here I have some pictures of examples. For example, these right here are metallic elements. They're metals. These are a few of them anyway. Aluminum, titanium, iron, copper. I can't see that one very well. Magnesium, zinc. So those are all examples of cubes of pure metals. All the atoms in each cube is one element. Here are some other examples. These 2 are pictures of the element iodine. Okay? Iodine, which stains things purple. All the atoms are one element, iodine. This one is sulfur. Whoops, I forgot the L. Sulfur. Okay? You find sulfur in match heads, but in that case, it's not pure sulfur. Pure sulfur looks like this. It's yellow. It can be a solid sort of a rock. In fact, that's how they mine it. It's a yellow, porous rock. And then they powder it, and they use it for different things. But it's a pure element. I believe this one right here is potassium. And I think this one right here is probably manganese. All right, these are pure elements. All of the sample contains only one type of atom. Okay? Now, about 90 of the elements out of the 118 that we have are found naturally on Earth. The rest of the elements are man-made in laboratories, and many are unstable and they only have a very short lifespan. In fact, some of them only last for fractions of a second when they bombard other atoms with different particles. Then all of a sudden they'll get a new element made for just a fraction of a second because it's very unstable and falls apart. But elements, 90 of them about, are found naturally on Earth. Now, if it's an element, the one place you can always locate an element is on a periodic table, which we'll be looking at before too long. Periodic table, or a table of the elements. If it's an element, it's on that table. If it's not on that table, it's not an element, okay? All right. So, now, what can we do with some elements? Here's another one that's used quite often, mercury. Notice that mercury is in spherical little blobs there. That's because at room temperature, mercury is the only metal that is a liquid at room temperature. Isn't that cool? Mercury is used in thermometers, not so much anymore. They've kind of gotten away from that because mercury is also highly toxic. It's also used in switches. For example, in a thermostat, when it gets too when the temperature gets too hot or too cold, the mercury slides to the other end of a little tube that tilts, and because it's a conductor, it switches on the air conditioner or maybe the heat. And so it's used a lot in switches. Dentists also use it in compounds for fillings. All right, some applications, other applications. Lead. All right, lead is used in the medical profession a lot. Do y'all know why? Well, lead is used to block radiation. Like when you have x-rays taken. Have you ever been to the dentist and they're going to x-ray your jaw or your teeth? And they take a big, heavy, sort of a cover thing, and they put it on top of you while you're sitting there, and that is to protect the rest of your body from the radiation. So radiation, which can be dangerous in large amounts, it's blocked by the lead because lead is very dense. Okay? It has a very high density. It's one of the densest metals. Okay? Aluminum. In England, they say aluminium. I don't know why, because there's not another I in there. So aluminium, But in any case, aluminum is widely used simply because of two things. It is bendable. Think about it. When your mother pulls out aluminum foil, she can easily bend it around the edges of a dish, a baking dish, because it's so bendable. She can just push it right into the corners or fold it over the edges. Makes it very handy to use. It's also resistant to corrosion. In other words, it doesn't rust like a lot of metals. So you don't have to worry about that. We also, of course, use it for lots of cans. Soda cans are made of aluminum. A lot of cans you get at the grocery store of food stuffs, they're made with aluminum. Graphite. Now, you've heard the word graphite before, but where can we find graphite? Well, one of the most common places to find graphite, which is carbon. Graphite is just pure carbon. It's used in pencils. Okay? The lead in your pencil is not really lead. Okay? It's actually graphite, and it's been used for several hundred years in pencils to be able to write with. They use it instead of lead, number one, because lead is also toxic. You can get lead poisoning from it. Graphite is not poisonous, Also, graphite is softer than even lead. Lead is a soft metal, but graphite is even softer, and therefore it will leave nice thick black lines when you write with it. Okay, so they use graphite in pencils to write. Okay? All right, so a pure element, all the atoms are alike. They're all the same kind of atom. Okay? Now, let's talk about the other type of substance right here, a compound. A compound is a substance in which you have atoms of two or more elements and they're chemically combined. They're bonded to each other. Okay, put that right there so you'll know later. They are bonded chemically to each other. You can't just pull them apart, guys. You have to do a chemical change in order to break them up. So, for example, here's a nitrogen oxide molecule. A compound in this small is these are molecules. So here we have a molecule compound of nitrous oxide. One nitrogen, one nitrogen, one oxygen, nitrous oxide. And here's water. You know, water is H2O. Well, here's the two H's. Here's the O, hydrogen and oxygen. They're bonded together, okay? Nitrogen dioxide. Here's your nitrogen right here, and here's your two oxygens. And here's carbon dioxide, which we find in our air as well. We've got carbon and two oxygens. Some other examples that we'll be using in just a moment. Salt, like table salt, is also a compound. It's sodium and chlorine together. All right? Then, of course, we just talked about water. Water is H2O. And then here's a different one, chalk, like old blackboards with chalk. Chalk is basically looks like this. CaCO3. We're going to talk about that in a moment. So, what are these made up of that makes them a compound? Salt is basically just what it shows right there. One sodium atom plus one chlorine atom. Now, it's interesting to note, by themselves, pure sodium is highly explosive, while chlorine in its natural form by itself is a gas. It's a yellow-greenish gas. Both of these together are highly poisonous and can kill you. But when you combine them chemically into a compound that we call salt, they're completely inactive. In fact, our bodies do need salt to survive, so it's kind of interesting that individually they're very poisonous, but together they're something we have to survive. Water is one oxygen atom plus two hydrogens. Okay, and you can't break them apart unless you chemically change them. All right, and then chalk, the actual word for this is calcium carbonate. It's one calcium atom plus one carbon plus three what? O is, well, what was the O here? It's oxygen, so it plus three oxygen atoms. Oops, that's not an O, that's a Q. I don't want that. I think I was trying to combine the O and the X. Okay, oxygen atoms. So a compound is just two or more elements chemically combined. You can't separate them physically. You can't just pull them apart with your fingers, okay? There's no way to do that. They are combined until you do something to them chemically to change that. All right, so a substance can be an element or a compound of elements. All right? Now, let's go to the other way matter can exist, and that's as a mixture. Now, a mixture is very different from a substance. A mixture is composed of two or more substances, and here's the kicker. They can be separated by physical means. You can actually pull them apart and separate them, okay? Now, there are two types of mixtures. Let's take a look. There are the heterogeneous mixtures, and these are mixtures in which the different materials remain distinct. For example, here we've got a chocolate chip cookie. The chocolate chips are distinct from the cookie part. Here you have pizza. The pieces of pepper, green pepper, are distinct from the pepperoni, or maybe the onions if there's onions on it. And you can actually pull them physically apart and separate them, okay? A sandwich composed of bread, lettuce, tomato, maybe a meat, you can pull those apart and they're individual again. They're separate. So that would be a mixture. Same thing with a salad. You can separate out the different parts. So a heterogeneous mixture is a mixture in which the different materials remain distinct. Some other examples would be sand in water. Another good one. How about, maybe you all eat this for breakfast. How about Raisin Bran? Okay, another example of a heterogeneous mixture. If you want to separate the raisins out, you can physically do it. They're not bonded to the bran flakes. The sand in the water, you can filter the sand out of the water. It's not bonded to the water, so they can be separated physically. All right, now let's take a look at the fact that there are actually, not only are there two types of mixtures, there's two types of heterogeneous mixtures. Don't worry, we're going to do a flow chart here at the end to help you keep all this straight. It's not that tough. Okay, the first type of heterogeneous mixture is called a suspension. Now, you guys kind of know what, in general, the word suspension means, right? The word suspension means it's sort of suspended in the middle of something, right? Like maybe a balloon suspended in the air. But it's a heterogeneous mixture made of a liquid and solid particles that settle. Okay, there's the kicker right there, that settle. An example would be salad dressing. If you let it sit there without shaking it, the solid pieces will separate from the oil. So that's a heterogeneous mixture because the bigger pieces can settle out, usually at the bottom. Orange juice is another example. The pulp in the orange juice. Some of you might like it with pulp in it. My dad doesn't. I always have to get him pulp free. So the pulp, the little bits of orange pulp that are in the juice are suspended, and they're larger particles than the rest of the fluid. So they can settle out at the bottom, and that makes this a heterogeneous suspension. You shake it back up and they move all over again, and then after a while they'll settle out. So suspensions have large particles that settle out. They can also be filtered. If you pour the orange juice through a filter, like a paper filter, then you can get the pulp out. Now, some other examples would be sand in water. If you put sand in a container of water and you can shake it, the sand particles will float all around, but over time they will settle on the bottom. So that is a suspension. Your Raisin Bran that we talked about a minute ago, that is also a suspension, okay? Because as the Raisin Bran is taken to market, by truck and train and plane and however it's getting there, the raisins will all settle down to the bottom of the box. Have you ever noticed that? You open a box of Raisin Bran and start pouring out and you realize, oh, all I see are flakes. That's because all the raisins have kind of shifted towards the bottom. Okay, so those are suspensions. The other type of heterogeneous mixture is a colloid. Now, a colloid is a heterogeneous mixture of a liquid and solid particles where the particles never settle. They always continuously float around in the liquid. They never settle out. Milk is an example. Milk contains protein molecules and fat molecules, and they never settle out. They just continually float around in the liquid. So that is a colloid, milk. Okay? Some other examples. Paint. Paint is made of different particles, larger, some smaller, and they never settle out. So every once in a while they do. If you leave it long enough, you might get an oil slick on the top, but paint usually doesn't settle out. So that is considered to be a colloid. Some examples that are a little different. Notice this says it's a liquid and a solid. We can also have a gas and a liquid. Watch this. What about fog? Fog is water particles suspended in the air. They're not falling like raindrops. Fog is a colloid, okay? Another example would be smoke. Smoke is also a colloid. When you have smoke particles in the air, they float around and they continue to float around. They never settle down to the ground. They just continue to float around. Smoke is a colloid. Now, what's a good way to tell the difference between a suspension and a colloid and a solution, which we'll talk about a solution in a minute? Well, a man named Tyndall discovered that colloids and suspensions, that is, heterogeneous mixtures, are different from solutions. They, when you pass a beam of light through them, they will scatter the light, and you can actually see the beam of light inside the fluid. Okay? How many of you have ever seen a beam of sunlight in the air? Same idea, only in this case, we're talking about light going through a liquid. When you flash it through a suspension, you can't see the light beam inside the solution. I said suspension, I mean solution. You can't see the beam of light inside the solution, but you can if it's a colloid or a suspension. The beam of light is scattered by the larger particles here, and we can see that beam of light then, okay? And that is called the Tyndall effect. And it's a good way for us to determine if something is a heterogeneous mixture or not, okay? Now, let's get down to the last type of last type of mixture. All right, we've looked at heterogeneous mixtures, both suspensions and colloids. Now, the other type of mixture that we might have is a homogeneous mixture. Homogeneous. That means the mixture remains constantly and uniformly mixed, and the particles are very small, so they cannot be seen without a microscope. They never settle to the bottom either. Another name for a homogeneous mixture is a solution. Now, what are some examples of solutions? Soft drinks, sodas are examples of solutions. A Coca-Cola has a mixture of different particles mixed in with the carbonated water, but they're so small you can't see them, and they stay mixed together uniformly so that when you look at your Coke, it looks uniform throughout the whole glass, okay? Tea, when you brew tea, that is also a homogeneous mixture or solution. The particles of tea that are mixed in with the water are uniformly mixed in, and they're so small you can't see them without a microscope. The only way you can tell that they are there is by the color, okay? Let's see. Now, here's an interesting one. Steel alloys. Now, this is not a solution per se, because steel is a solid. But if you have a steel alloy, steel is made of iron mixed with other metals. And those other the atoms are mixed inside with the iron, there's some iron, they're like in a structure. So you'll have iron, aluminum, copper, iron, aluminum, copper, iron, aluminum, copper in the lattice structure. So that is also a mixture, and it's a homogeneous mixture because it's uniformly mixed all the time, and the particles are so small that they can't be seen without a microscope. So steel could be considered a homogeneous mixture. Salt water is also a homogeneous mixture. Okay? When you mix the salt in, now here's where you get a chemical change. The water acts to dissolve the bond between the sodium and the chlorine ions, so you get water with free-floating sodium ions and free-floating chlorine ions. So you've chemically unbonded those. So it's no longer it's no longer a compound. It's now a mixture, all right? And the salt water, you can't see the salt particles. They're too the chlorine and the sodium ions, they're too small, and it stays uniformly mixed. And of course, here's some other examples, except for the orange juice with no pulp. Okay, orange juice cannot be a homogeneous mixture unless all the pulp is removed, and then it can be considered a homogeneous mixture. Okay, now, so we've got substances that can be elements or compounds, and we've got mixtures which can be heterogeneous mixtures like suspensions and colloids, or they can be homogeneous mixtures or solutions. Let's make a flow chart to help us understand the different, or the way that it's all related. Okay, so don't you love the colors on this? I just thought this was the neatest thing. So I sort of stole it off the internet. In any case, we start with matter. All matter is divided into one of two categories. They're either substances or they're mixtures. Okay? Now, if it's a substance, it's one of two things. It's either an element. Notice individual atoms that are all the same atoms. Or it's a compound of elements. That means they're chemically bonded. Okay? So here you have one big atom bonded to two like smaller atoms. So they are chemically bonded. You cannot physically separate them. It would take a chemical reaction to separate them, okay? Now, if it's a mixture, it could be, let's start with this one over here because we talked about it first. Heterogeneous. Well, that's a big word for a small rectangle. It could be a heterogeneous mixture. All right. Sometimes it is, and we're going to add to this one, sometimes the heterogeneous mixture can be a suspension. And that's when, if you'll remember, the particles can separate physically. They can settle out. You can even remove them by filtering or just by plucking them out, okay? Now, the other type of heterogeneous mixture can be a colloid. Oh, I'm sorry, I didn't realize you could see that. There we go. Is that better? I apologize. I'll give you a moment there to copy that down. All right, so we said a heterogeneous mixture can be a suspension where the particles can separate physically, or it can be a colloid. In the case of a colloid, the particles never settle out. Now, they can be physically separated, like with a filter, but they're not going to settle to the bottom of the container that they're in like they would with a suspension, okay? They're not going to do that. Milk, the fat particles and the fat molecules and the protein molecules, they're going to stay suspended or moving around through the liquid of the milk. They're never going to settle to the bottom like they will with a suspension. So that makes milk a colloid. All right. Now, the other type of mixture is the homogeneous mixture. Now, homogeneous mixture, remember, is another name for solution. So these are also solutions. And notice the particles stay suspended uniformly throughout among each other. Okay? They never separate. That's what homogeneous means. It is uniform throughout. And the big difference between mixtures and substances, mixtures can be separated. The constituent parts can be physically separated. But substances like elements and compounds, you can't do that. All right? They have to be chemically separated. All right. So, there we go. Composition of matter, substances or mixtures, and the different types. Okay? All right. See you soon. Bye-bye.